Infinite intervals and interval length. Welcome, everyone. Before we dive into today's new topic, let's take a moment to reflect on what we have already covered. In our previous lessons, we focused on what we call finite intervals. As you remember, these are intervals where both the starting point and the ending point are specific, fixed real numbers, meaning they have a clear beginning and a definite end. However, mathematics isn't always contained within such boundaries. In many mathematical scenarios, we encounter sets of numbers that don't just stop, they extend indefinitely, either in one direction or even in both directions. When a set of numbers continues on forever without a boundary, we refer to these as infinite intervals. Today, we are going to learn how to represent these and how to work with them. Understanding infinite intervals. Now that we've established that we are moving beyond finite intervals where both ends are fixed numbers, let's dive deeper into what actually defines an infinite interval. Think of an infinite interval as a subset of the real numbers, which we denote as R, that lacks a boundary on one or both sides. Unlike the finite intervals we studied previously, these sets don't just stop at a specific value, they keep going. To mathematically represent this idea of going on forever, we use the symbol infinity for the positive direction and negative infinity for the negative direction. But I want you to pay very close attention to this next part, as it is a common pitfall for many students. It is vital to remember that infinity is not a real number. It is a concept representing a value that increases without bound. Because infinity isn't a specific destination you can actually arrive at, we can never truly include it in our set. Therefore, when you are writing your notation, you must always use a parenthesis, either an opening or a closing one, with infinity or negative infinity. You will never, ever use a square bracket with these symbols, because those endpoints can never be reached. Keep this rule in mind, because in the next slide, we are going to look at some specific examples of how this notation looks in practice. Common types of infinite intervals. Now that we understand the concept of infinity as a direction rather than a specific number, let's look at some common types of infinite intervals you'll encounter. I've broken these down into three main categories. First, let's look at non-negative real numbers. This set includes 0 and every positive number following it. In notation, we write this as a closed bracket 0, followed by an open parenthesis infinity. If we were to translate this into an inequality, we would say it represents the set of all x, such that x is greater than or equal to 0. Visually, if you were looking at a number line, you would see a solid dot at 0. Because of that closed bracket we discussed earlier, and then an arrow pointing forever to the right. Next, we have negative real numbers. Unlike the first example, this set includes only numbers that are strictly less than 0. We represent this using an open parenthesis negative infinity, followed by an open parenthesis 0. In terms of meaning, this is the set of all x, such that x is less than 0. On your number line, this interval comes from the far left, starting from negative infinity and moves toward the right, stopping just before it reaches 0. Notice we use an open parenthesis at 0, because 0 itself is not part of this specific set. Finally, we have the most expansive interval of all real numbers. This encompasses every single possible value on the entire number line. We denote this as an open parenthesis negative infinity, followed by an open parenthesis infinity. Mathematically, this means negative infinity is less than x, which is less than infinity. This interval covers everything, and it is exactly equivalent to the set of all real numbers, which we denote with a capital R. As we move to the next slide, we will shift our focus from how these intervals are defined to how we calculate the distance, or the length, between endpoints in finite intervals. Interval lengths. Now that we understand how to represent intervals that extend forever, let's shift our focus to a property that applies to our finite intervals, the concept of interval length. Think of the length of an interval simply as the distance between its two endpoints on the number line. To calculate this, let's look at any finite interval, meaning one that doesn't go to infinity, defined by a lower bound, which we'll call a, and an upper bound, which we'll call b, where a is less than b. To find the length, you simply find the difference between these two values. The formula is straightforward. Length equals b minus a. And here is a very important point to remember. This formula works every single time, regardless of the type of interval. It doesn't matter if the interval is open, using parentheses, closed, using square brackets, or even half open, like a mix of both. The distance between the 2 points remains the same. We will see this applied in a practical, real-world example in the next slide. Real-world example, temperature range. Now that we have covered the theoretical formula for finding the length of an interval, let's move away from abstract numbers and look at how this applies to a real-world scenario. Imagine a scientist is monitoring the temperature of a chemical reaction. To ensure the reaction is successful, the temperature must be maintained between 15.5 degrees Celsius and 22.8 degrees Celsius, inclusive. Let's walk through the step-by-step calculation to find the length of this temperature range. First, we need to identify the interval. Because the problem states the range is inclusive, meaning the temperature can be exactly 15.5 or exactly 22.8, we use square brackets. So, we write this as the closed interval, 15.5 to 22.8. Second, let's identify our endpoints. Our lower bound, which we'll call A, is 15.5. Our upper bound, which we'll call B, is 22.8. Third, we apply the formula we learned on the previous slide. To find the length, we subtract the lower bound from the upper bound, or B minus A. In our case, that is 22.8 minus 15.5. Finally, we calculate the result. 22.8 minus 15.5 gives us 7.3. So, the total length of this temperature interval is 7.3 degrees Celsius. As we move to the next slide, keep this calculation in mind, because I'll show you some common pitfalls where students often make mistakes when working with these types of intervals. Common mistakes to avoid. First, let's talk about using square brackets with infinity. You might see someone write something like 0, closed bracket, infinity, closed bracket, or negative infinity, closed bracket, 5, closed bracket. Both of these are mathematically incorrect. The correct way to write them is 0, closed bracket, infinity, open parenthesis, or negative infinity, open parenthesis, 5, closed bracket. The reason for this is very important. As we discussed earlier in the lesson, infinity is not a specific real number that we can reach or touch. Because we can never actually arrive at infinity, we must always use an open parenthesis to show that the interval is unbounded. Second, be careful with the order of subtraction when calculating interval length. I have seen students attempt to calculate the length as a minus b. This is a mistake. To ensure that your result is always a positive value, which is essential since distance cannot be negative, you must always subtract the smaller number, which is your lower bound, from the larger number, your upper bound. So, always use the formula b minus a. Finally, a quick note on trying to calculate the length of infinite intervals. Sometimes, beginners try to apply our subtraction formula to an infinite interval, attempting something like infinity minus 0. While it might seem like a calculation, the mathematical fact is much simpler. The length of any infinite interval is simply considered to be infinite. Now, before we wrap up today's lesson with our final summary, I want to pause and highlight some common pitfalls. Even students who understand the concepts well can sometimes make these 3 mistakes, so please pay close attention. Keep these points in mind, and you'll avoid the most common errors in this topic. Now, let's move to our final slide to review the key takeaways. Key takeaways. First, remember that infinite intervals are used when a set of numbers doesn't have a fixed end. We use the symbols infinity and negative infinity to show that the set continues forever in a specific direction along the number line. Second, this is a crucial point for your notation. You must always use parentheses, not square brackets, when writing infinity or negative infinity. Because infinity is a concept and not a specific reachable number, we can never truly include it in the set. Third, if you want to represent every single possible value on the number line, which we call the set of all real numbers, denoted by the symbol r. You can write this as the interval from negative infinity to positive infinity, using parentheses on both sides. Finally, when dealing with finite intervals, don't forget how to find the distance between 2 points. The length of an interval is simply found by taking the upper bound, b, and subtracting the lower bound, a. Just remember to always subtract the smaller number from the larger one to keep your length positive. All right, we have reached the end of our lesson. Let's take a moment to recap the key takeaways to ensure everything we've covered today is clear. I hope this summary helps solidify these concepts. Great job working through these slides with me.